This lecture will address the physical chemistry of the halogens. Emphasis in this lecture will be placed on the physical chemistry of chlorine because it is, by far, the most commonly used disinfectant in wastewater disinfection applications. But it's important to recognize that the physical chemistry of chlorine extends and in fact translates quite well, in most respects, to the physical chemistry of the other halogens. So I'll present some information that can be generalized among the halogens, again with a focus on chlorine as the example in this lecture. The halogen family in the periodic table includes the elements fluorine, chlorine, bromine, iodine, and astatine. They are, in fact, what are known as the group 7A elements, and they have 7 valence electrons, which yields very similar chemical behavior among each of the elements that we identify as the halogens. Among those halogens, the most commonly used for disinfection are chlorine, bromine, and iodine. The general molecular form for the halogens is X2, where X represents any one of these halogen atoms. The fundamental equilibria that define the speciation of halogens in aqueous solution is important to understand. It starts by a reaction between the halogen molecule X2 and water to yield the hydrated form of X2, or the aqueous form. In turn, aqueous halogen molecules will react with water through a hydrolysis reaction to yield a hypohalous acid, HOX, and a hydrohalic acid, HX, which tends to be a strong acid. The equilibrium for this reaction, which tends to be fast in both directions and therefore allows equilibrium conditions to be met very quickly, is defined by a hydrolysis constant, and the mathematical description of that hydrolysis constant follows the general convention for all equilibria. The hypohalous acid, HOX, generally will exist as a weak acid, and so under normal conditions it will dissociate partially, and the extent of dissociation will depend on the pH. The acid dissociation constant for this reaction is again defined using the conventional equilibria, and again, because these reactions are fast in both the forward and reverse directions, for most practical applications they can be considered to be at an equilibrium condition. Therefore, pH is going to play a very important role in governing the distribution of the various forms of the halogens in solution. The halogen atom, again, is usually going to be defined as X, and the most common forms of the halogen atom that we see in disinfection applications include chlorine, bromine, and iodine. As I mentioned before, HOX represents a hypohalous acid, generally a weak acid, and HX represents the hydrohalic acid, generally a strong acid. K sub H and K sub A, respectively, represent the equilibrium constants for these two reactions, hydrolysis constant and an acid dissociation constant. Here's an illustration of the equilibria that represent chlorine and its distribution in water. In the left column are the various reactions that define the equilibrium distribution of chlorine among its various forms. And on the right are the corresponding equilibrium expressions with values for the equilibrium constants that have been reported at 25 degrees C. Among these various forms, we find 5 different forms of what we can identify as free chlorine. They are molecular chlorine, Cl2, hypochlorous acid, HOCl, the hypochlorite ion, OCl-, chlorine monoxide, Cl2O, and the trichloride ion, Cl3-. Again, these 4 equilibrium expressions allow us to quantify the distribution of chlorine among these various forms in solution. And because all of these reactions are rapid in both the forward and reverse directions, they come to equilibrium relatively quickly. That allows us to do some calculations of the distribution of chlorine among these various forms as a function of solution chemistry. As an illustration, consider this graph, which illustrates the distribution of chlorine among its 5 different forms for tap water. In this calculation, I've assumed a chloride concentration of 10 to the minus 4 molar, which is sort of representative of a tap water sample. I've assumed also that we've applied 5 milligrams per liter of chlorine as Cl2, and this experiment is assumed to have taken place at 25 degrees C. In this graph, it's important to note that the vertical axis, and for that matter, the horizontal axis, are both on a log scale. The scale on the vertical axis is perhaps easy to see, but it's important to recognize that pH itself is a log transformation of the proton activity, and therefore pH is also a log scale. So in fact, this graph represents solution composition over incredibly broad ranges of concentration. If we consider the range of pHs that's normal for most wastewater treatment applications, typically somewhere between 6 and 9, what we see here is that the residual chlorine, free chlorine in this case, is dominated by HOCl and OCl-. The other three forms of residual free chlorine are present at trace concentrations, orders of magnitude lower concentrations on a molar basis than either HOCl or OCl-. We also see that the distribution of free chlorine between HOCl and OCl- is governed strongly by pH. In particular, when the pH is above the pKa for hypochlorous acid, about 7.6, we see that the residual chlorine is dominated by OCl-. That's indicated by the green line here. And for pH conditions less than the pKa of HOCl, we see that HOCl is going to dominate, and that's the red line here. If we were to consider another example of a water that might be chlorinated, specifically seawater, the biggest difference that we see between seawater and tap water is the chloride concentration, at least in the context of these reactions here. In this case, the chloride concentration is several orders of magnitude higher than it is in a tap water sample. If you go back and look at the reactions that are responsible for the distribution of free chlorine among its various forms, chloride plays a really important role. So if again we go back to the typical range of concentrations that we observe, 6 to 9, we observe that still HOCl and OCl- are going to dominate. But in this case, we see that Cl2 and even the trichloride ion can contribute, although their concentrations tend to be several orders of magnitude lower. Now that's relevant in some circumstances because Cl2 is sometimes a much more effective reactant than either HOCl or OCl-. So there are some reactions for which this chemistry actually plays an important role. Now let's consider the behavior of chlorine or the other halogens more broadly as chemical disinfectants. They tend to accomplish microbial inactivation by inducing chemical damage to one or more critical biomolecules. But the nature of these reactions between chlorine and the various constituents of microorganisms, for example, a bacterial cell as illustrated here, tend to be pretty broad-ranging. So the damage tends to be non-specific and cover many different critical biomolecules or even functional units within a bacterial cell. If we think more broadly about halogens, including chlorine, and how they react with other things that are present in solution, the halogens tend to participate in two general types of reactions: oxidation-reduction reactions, in which there is electron transfer, and substitution reactions, in which there is no electron transfer. The ability to accept electrons is quantified using the standard redox potential, and that allows us to identify and understand a little bit more about the behavior of the halogens in solution. Let's consider then the standard redox potentials for the various forms of free chlorine that are dominant. Molecular chlorine, or Cl2, shows a standard redox potential of 1.36 volts. Hypochlorous acid shows a standard redox potential of 1.49 volts, and the hypochlorite ion shows a standard redox potential of 0.9 volts. Now you'll notice that in each of these reduction half reactions, there are two electrons that are participating with each of the forms of residual chlorine. So what that means is that each mole of these forms of free chlorine has the ability to accept 2 moles of electrons. Because of that, we refer to these forms of free chlorine as being electrochemically equivalent in that they have the same ability to accept electrons. It's important to recognize that the ability of a molecule to accept electrons is not the only thing that we care about. In fact, the standard redox potential provides an indication of the driving force for electron transfer to take place. So even if these molecules are electrochemically equivalent, it turns out that HOCl is the strongest oxidant among these forms of residual chlorine because it has the highest standard redox potential. The definition of free chlorine generally that we find in the literature focuses on HOCl and OCl-, and that's because these are the dominant forms of free chlorine under most conditions, as illustrated early in this presentation. But we need to recognize, as I tried to emphasize previously, that molecular chlorine can sometimes be a relevant contributor to the behavior of residual chlorine, especially under conditions of low pH and/or high chloride ion concentration. Because of that, the formal definition of free chlorine is the sum of the molar concentrations of these three dominant forms. By extension, what that tells us is that we generally ignore the contributions of chlorine monoxide and the trichloride ion, and in some circumstances we choose to ignore the concentrations of molecular chlorine, or Cl2. The definition of free chlorine is based on electrochemical equivalence, and since each of these forms of free chlorine is electrochemically equivalent, they're identical in their contributions on a molar basis to the amount of free chlorine that we have in solution. We simply add up their molar concentrations, and that yields the free chlorine concentration. Sometimes people choose to express the free chlorine concentration as equivalent mass concentration by multiplying this molar concentration of free chlorine by the molecular weight of Cl2, and that molecular weight is 70.9 grams per mole. Summarizing then, we've seen that the halogens include fluorine, iodine, chlorine, bromine, and astatine. And among these, the most commonly used forms in disinfection are chlorine, bromine, and iodine, and in fact, in wastewater disinfection, chlorine is dominant. The halogens themselves have similar chemistry, and that's because they are part of the same family, the halogen family, in the periodic table, where we have 7 valence electrons. The reactions that are responsible for speciation, or more formally distribution, of halogens in water tend to be rapid, and they reach equilibrium quickly. The halogens participate in 2 general types of reactions, redox reactions and substitution reactions, and the ability of molecules, including the various forms of halogens and free chlorine, to accept electrons is defined by these reduction half reactions and their standard redox potential, which describes the driving force for electron transfer. Compounds that have a large driving force for electron transfer tend to be powerful oxidants. And lastly, the definition of free chlorine is based on electrochemical equivalence.